starting a new unit. And so the first thing that I want to take care of, which is kind of like a short little bit, is I'm going to talk about units and rings, and then I'm going to do Kaylee, Hamilton, and Nakayama. So yeah, so let me I'll say a little bit about Nakayama when I get there. So so this is about units and rings. So units, absolute units. Okay, units in rings. Okay, so again, the group of units is the multiplicative group of invertible elements in a ring. Okay, so I'm going to first do it for local rings, and then I'm going to show this thing about Jacobsen radicals, and then I'm going to do the kind of general statement. So and these kind of proofs are really common for qualifying exams. So someone can ask you to prove this. So lemma. So let Rm. Okay, maybe I should just do, this is a Fraktur M, be a local ring. Okay, so in the case of local rings, right, the units are just everything not in the maximal ideal. Okay, so the group of units is just everything not in the maximal ideal. All right, so let's do the proof. So the proof is pretty straightforward. So if and I just want to remind you that maximal ideals are not R, right? In particular, they're a sub R module of R, a proper R submodule. So they can't be the full ring. Okay, so if X is a unit, and I guess I should remind you that a local ring is a ring with a unique maximal ideal. Okay, so all the rings are contained in this maximal ideal. So if R is a unit, right, then we have that X is not contained in the maximal ideal. Otherwise, R would be equal to the maximal ideal, right? And so this would, you know, this would be a contradiction. Okay, so this proves one direction, right? So this proves that that R, this thing is, the units are not contained in the maximal ideal. Okay, so conversely, if X is not a unit, right, then this is an ideal, right, is a proper ideal. And it's contained in a maximal ideal. And since there's a unique maximal ideal, it has to be contained in M, right? So what we just showed was that, so if X is not a unit, this showed that X is an element of the maximal ideal. This is equivalent to the contrapositive of the statement, which is saying that if X is not an element of the maximal ideal, then this implies that X is a unit. Sorry, X is not a unit, right? And so this is the same thing as saying that that R set minus the maximal ideal is contained in R cross.
Can I ask a quick question?
Yeah.
It kind of seems like what you know, is it we talk about chains of ideals a lot. Is there like all chains end with that unique maximal ideal then?
Yeah,
I guess?
all chains will end with that unique maximal ideal. That's correct. That's correct. It is, yeah. All chains will end there. That's true. Right, so like examples of local rings, right? ZP power series, you know. So examples of local rings again. You know, ZP of local rings. ZP power series in many variables. You know, what else? I mean, so for any prime P, prime ideal P, RP. This was like SP inverse R is a local, you know, this is one here. SP is R set minus P. So like this gives you a ton of examples. Okay. All right. In a ring A. So okay. So this is so now we have the units for local rings. Okay. So we can beef this up a little bit.
On those examples, R would like if you have C the power series there, that the R that's R itself. Like what would be its unique maximal ideal?
So the unique max for this example here.
For like the series in XYZ.
Oh, so the unique maximal ideal here, M is XYZ. And for this one here, M is P. And for this one here, M is P times A of P.
What about shifting like X minus 3, Y minus 2, Z minus 1? That's not a...
So like X minus 1 is like if in here, so if I did, so note that like if I did X minus 1 here, all right, so this is negative 1 minus X, and this is, and so 1 over 1 minus X, this is 1 plus X squared. So in this ring, in C, X, Y, Z, 1 minus X is a unit.
Wow. Okay. Interesting. Thanks.
Yeah. So like all the other translates, yeah, you know, like any other translate like that, you know, these ideals, X minus A, Y minus B, Z minus C, for A, B, C in C cubed are not maximal ideals. If A, B, C is not equal to 0, 0, 0. Yeah. So another thing about this ring here is this is really the other thing about this is that this thing here is really the completion, the inverse limit of AP mod P. Let's call this M P to the n, where MP is XYZ times the XYZ times C of XYZ localized at this ideal. Okay, and A here is C of XYZ. So this one's really, this is the completion. So of AP. So yeah, so completions of local rings are local rings. Okay, maybe that's a good exercise. All right. Good questions. Okay, so I'm gonna kind of improve this. So this is the local ring case. Any other questions about this before I move on? Thumbs. I'll assume that you guys are all giving me the thumbs up. All right. So, okay, so now let's kind of build on this, right? And so we're gonna start building towards a general version. We don't really need, I guess. statement. Okay, so to do this, I need to introduce a definition. I guess I don't need it for the completely. Let me just give you a spoiler. I don't know. Okay, let me just do this. This is kind of something that comes up all the time. Okay, it's not the most general version, but it comes up enough that I want to do it. Okay, so the Jacobsen radical. Okay, so the radical was like the intersection of all prime ideals. Is this ideal? I'm going to call it Jacobsen radical. JRAD is M in. So these are the maximal ideals. So it's just the intersection of all maximal ideals. Okay, and so let me just kind of, for comparison, right? So recall that, so, you know, for a prime ideal, so the formulas are kind of similar. Let's do it like this. Let's write the intersection over a set. P contains I. P contains I. So I guess the nil radical, right, was the intersection of so instead of intersecting all prime ideals, I intersect all maximal ideals here. Okay. And I guess you could intersect over minimal prime ideals here and get the same thing. So they're not the same, right? So these are not the same. So this is intersecting over fewer things. Okay, anyway, let's prove a theorem. Okay, so let J be the Jacobsen radical of R. Okay, so if X is an element of 1 plus J, then X is a unit. Okay, so this gives a version of that. So like in this example, you know, anything in 1 plus M would be from the previous theorem. Any element of the form 1 plus M would be in the units here, and so this is kind of a generalization of that statement. Okay, so the proof. Okay, so the proof of this is by contrapositive. Is contrapositive. So okay, so if X is not an element of R cross, then this implies that X is not an element of 1 plus J. So these proofs are relatively easy once you know kind of like the right statement to prove. So sometimes when you're stuck trying to prove something, right, you just gotta like try the contrapositive and try like all the different versions of proof, you know. And sometimes one of these looks a lot easier psychologically than another one. And that's kind of I find that to be the case with these sort of statements here. Okay. Anyway, so we'll prove this by contrapositive, right? Okay. So if X is an element of R cross, then X is contained, not an element here, then X is contained in M or some maximal ideal ideal M. So we proved this a long time ago. This is like maybe the first or second class where we did this axiom of choice business. That's what we had to do. We used the axiom of choice to prove that. Okay. So if we also have x is in 1 plus j, then since j is contained in M, we have x is an element of 1 plus M. So this means that x looks like 1 plus like some M for little m. Okay, let me not use M here because I have a feeling that some people might be using have not wanted me to use did not want to write the fraktur. So let's do 1 plus A for A in this thing. Okay, so let's do that, and then now we have X as an M and A as an M, right? So this implies that 1 is equal to X minus A, which is an element of M, which proves that M is equal to R, which is a contradiction. Because remember, maximal ideals are not the whole thing. All right, so all right, that gives us the contradiction that we need, and we're done. Okay, so it's kind of the same deal. You're using the property that elements are contained in non-unit elements are contained in maximal ideals. All right. So one of the crazy parts about these proofs is that it gives us no way of writing down the inverse. So just kind of a funny observation. Is that both these proofs, both proofs, oh, dang it, I forgot to mute my Discord. Both proofs, so DZB was saying that he was gonna like spam my, I told him that I accidentally leave my Discord on sometimes, so he said he was gonna try and spam my Discord. So, okay, anyway, hopefully he stops. Okay, so both proofs don't give you a formula, so don't, give you no way of writing down inverses, right? So this is an example of something that's like really indirect, right? It's like we know that it's invertible, but we don't know what its inverse is, right? Okay, so all right, so now let me just give the general characterization. Of units. Okay, so theorem. Let R be a ring. Okay, so X is a unit if and only if X is not contained in the union of maximal ideals. Let me see if did I write this? I just wanted to check for the Jacob. Okay, yeah. I wrote this as a capital M, but that's okay. I thought I would. Anyway, okay. All right. So this is what we have. So it's not in the union of anything. Okay. So let's do the proof. The proof is like the other proofs. So proof. Okay. So we're going to do the negation. So we will show that X is not an element. It is not a unit if and only if X is in the union of maximal ideals. Okay, so let's do this direction. So if X is not a unit, right, then what do we do? So then X is contained in M for some maximal. That's done. Okay, so this direction, right? If X is in the union of the maximals, then X is in some particular maximal ideal, a maximal ideal. And so if X were a unit, then X would be in so if X were a unit, then if X were a unit, then M this M0 here would be equal to all of R, which is a contradiction. So they're all pretty basic proofs. They all go the same way, right? So the two things that you use is that proper ideals can't contain units, and non-units are contained in a maximal ideal, right? And that's all I have to say about units. Okay, so does anyone questions before I move on to Cayley Hamilton?
There were no assumptions on that. On the
No assumptions on the
Yeah.
ring at all. Totally general.
And that's the case with the previous theorem too, right? I think.
Yeah, the previous theorem is no assumptions at all. Yeah. But for some reason, books never write down this one. Like there's a lot of books that don't use this, they use this, right? But this is less general, right, than this one. And it's just as easy.
The notion of to be Jacobsen seems to come up too. I don't know if it's like a prime ideal is Jacob, or no, a ring. Never mind. I forgot.
There's a thing called Jacobsen rings, but I don't remember what they are. Right. This in the context of units is usually where I see this hypothesis. Yeah. Okay. So there's also this like Zariski-Nagata theorem that uses this sort of thing, but yeah. But I don't remember what that says exactly. I don't off the top of my head. Okay. All right. So now let's do Cayley Hamilton. Okay, so Cayley Hamilton in Nakayama. You know, I was writing notes for this, and just like the Hamilton song is stuck in my head now. My name is Alexander Hamilton. Anyway. Okay. Okay, so I guess we'll do let's do Cayley Hamilton first. Okay, so Cayley Hamilton, you guys know the statement before. So it's about the annihilation of so like if you take the characteristic polynomial of a matrix and then you plug the matrix into it, that it's going to kill the matrix. Okay. All right. So and we're going to kind of do a general version of this where we use, instead of vector spaces, we're going to use modules, finitely generated modules. Okay. All right. So and so first we need to recall a linear algebra fact. Okay. So you probably haven't seen this in this form before, but we're going to let R be a ring. Okay. I mean, you've all seen this, but maybe you don't know that you've seen this. Okay. So let A be an n by n matrix. Okay, so there exists, so there's a matrix here, which we will call A tilde, or the adjective matrix, right? So there exists this matrix. An adjective matrix. Let me do it. Actually, let me do this a little bit better. Okay, so this is for any matrix in the world, in any ring, of course, commutative with one. There exists a special adjective matrix. Here, and we'll call this A tilde, or the adjective of A. This is an n by n matrix with the property that well, A tilde times A is equal to A tilde, which is the determinant of A times the n by n identity matrix. Okay, so the idea is that this matrix is kind of like the inverse matrix, but before you divide by 1 over the determinant. Okay, so the formula for this for the adjective. So the formula is that the adjective of A transpose is equal to -1. So if I do this, and then I look at the ijth entry, this is 1 or I plus j times mij, where this is the determinant of the minor of A, where we delete the jth row, or the jth column in ith row. Okay, so this is the okay, again, this is like the inverse matrix, right? Where, except for you don't have the determinant term, right? So it's kind of like every matrix has a matrix inverse, except you don't really get the identity. You get the identity with a bunch of determinants on it. Okay. So you just use the formula for the inverse matrix. So the formula for the inverse matrix, you just use the formula for the inverse matrix, but multiply by the determinant, and that's how you get this adjective matrix. Okay. So now we're going to use this to prove Cayley Hamilton, and this works for any ring. It doesn't have to be a field. Doesn't have to be anything. Okay. It has to be n by n. That's the constraint. Okay. So now let's prove the theorem. So let's do the Cayley Hamilton theorem. Okay. So let M I redid these notes somewhere else. Oh. Huh. Anyway. Okay. So let M be a finitely generated R module. Okay. And let phi be an endomorphism with the property that phi of M is contained in I of M, where I subset of R is an ideal. Okay, then the matrix then there exists. Let's put it this way. Then the polynomial. Well, I guess I have to write it. I have to say what it is. It depends on generators. Let's just do it this way. Then there exists a polynomial. Let's say x to the n plus a1 x to the n minus 1 plus dot dot dot. I'm writing it a little bit backwards. An such that, let's call this p of x, such that 1, p of phi is equal to 0, and 2, that ai is an element of I to the n minus I.
Can I ask about I times m?
And n is the number of generators here. Yeah, let's yeah.
So I times m, I'm just kind of thinking like it's not necessarily, so if m is a vector space, would that be like just restricting the scalars, like the number of things that are scalars, or what is I times?
So I am, let's talk about that. So what is I am here? So I am
Is it a subspace if it was a vector space?
The set of am, where a is an I and m is an m. So it's an R submodule. So this is an R submodule of m. So in particular, right, if m is generated by let's say m1, m2 up to mn, then the elements of im look like a1 m1 plus a2 m2 plus an mn, where the AIs are an I. Does that make sense? So it's just everything in the module, like you were saying, everything in the module, but with coefficients in the ideal.
Yeah, it makes sense. And if it was when you say R submodule, that's the generalization of a subspace in the vector space world, right?
Yeah. Okay. So it's an abelian subgroup that is closed under scalar multiplication. And scalar multiplication is multiplication by R.
Awesome. All
right. Yeah. Okay. So this is the theorem here. Okay. So let me. I'm a little worried about this here. So because I don't know. I thought I rewrote the notes with the different. Let's see. With the different notation. I hate writing polynomials like this for some reason. But we'll see. We'll see what happens. My notes. I don't know why I did this. Okay. All right. So here's the proof. All right. And so the spoiler is like. So let me just also say that this is going to be the characteristic polynomial. This is going to be like the characteristic polynomial of some matrix. Okay. Well, I mean, I shouldn't put it in quotes. It will be the characteristic polynomial of some matrix A. Okay. And so I'll show you how to get this matrix. Okay, so so what we're going to do is we're going to let M1, M2 through Mn be generators of M. Okay, then since phi of M is an IM for all M in M, so we just get to write out what phi of M is, right? So phi of M, Mj, looks like a sum of aij's, xi's, for I is equal to 1 up to n, where the aij's are in I. Okay, so all right, so it'll be useful in what follows to maybe write this in our R of X module notations. So in our notation where M is viewed as an R of X module in R adjoin X module. So this is the module where multiplication by X is an application of phi, right? We have X Mj is equal to, oh, sorry, this should not be an Xi, this should be an Mi here, is the sum from I is equal to 1 up to n of aij mi. Okay, so what does this mean? So this means that here we have the sum from j, so from I is equal to 1 up to m, or up to n, of, now we can do delta ij x minus aij, this thing times mi is equal to 0. Okay, so this thing is so this is so what is this guy here? This is the Chronicler Delta.
I didn't see. Do you have that XMJ and MJ itself are both the same linear combination? Maybe you changed something.
So here I'm using the fact that I'm using the Chronicler Delta here. So the sum over delta ij.
Right, but I mean above. I think when you wrote out that the MJs are linear combinations. Oh, sorry, phi of MJ. I'm sorry. Okay, sorry about that.
Yeah, that's what this is, phi of MJ. In the notation, we're reviewing this as a R of X module.
Okay, I need to pull up the app. Thanks.
Yeah. So yeah. So this thing here is equal to 0 when I is not equal to j, and 1 when I is equal to j. And so you can rewrite it this way, okay? And so so this is actually a system of equations, right? So this is a system of equations. And this gives us essentially the identity x minus a, and then we have this thing here, m1 mn is equal to 0. Okay.
Do you mind if I'm sorry, when you have that that phi is always represented by multiplication by some x.
Yeah.
What's going on? So since it's an R of X module.
Yes, the R of X module structure is that if I have, if
all homomorphisms are represented by polynomials, basically, or
well, yeah, scalar multiplication. So if f of x is an R of x, So we and m is an m. So we define that f of x times m to be f of phi applied to m. So this thing will look like b0 plus b1 phi of m plus b2 phi squared of m. So this is the iterate plus dot 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 plus I don't know bd phi d of m, where if f of x looks like b0 plus b1x plus b2x squared plus dot 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 plus bd x to the d. So this is like the multiplication is that yeah. Does that make sense?
It does, and ours is just x itself.
Yeah, we're just looking at the single application of x.
Because then we can extrapolate up to an arbitrary polynomial. Or
yeah, the only reason I'm doing it like this is because I want it to look like something familiar to you guys. That's why I'm writing it like this. So okay. It looks like a characteristic polynomial, right? So we have this system here, and so what we can do is we can multiply, right? All right. So we read it as a system here, and now we can multiply by the adjective matrix, right? On the left by the adjugate of xi minus a to get here. So we'll essentially get the determinant of ix minus a. So this thing here times the identity, the n by n identity matrix of m1, m2 here, mn is equal to 0. And so this implies, so this is just a scalar, that the determinant of ix minus a, and then what was I using? Mi. This thing mi, or let's say mi is equal. It doesn't matter. We could use anything here. Mi is equal to 0 for all I. So for all I here. Okay, so this is what we have. Okay, and all right. So this shows that that this kills. So this is the polynomial. So this is the polynomial here. P of x in the statement. All right, and so okay, so what we'll have now we need to look at the coefficients. So P of x looks like, okay, let me like b0 plus b1 x plus dot 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 plus bd x to the d here. I guess this will be Monica. Bd x to the d. Okay, so what's happening here is that this thing will be, so this is a product of a sum of a product of products of n elements of I. So this is an element of I to the n. So this is a sum of products of n minus 1 elements of I, right? So this thing is an element of, this is an element of I to the n minus 1. Okay, and so on. So so we'll have, so in general, bj will be an element of I to the n minus j. Okay, so in the statement, let's just make sure that we had the statement right. That's what I was worried about at the beginning. Okay, so maybe, so this should be since it's backwards. It should be I think. Yeah. So this is the correct statement here. Okay, so with the polynomials reversed there. Okay, and that's it. That's it. Okay, that's the proof of Cayley Hamilton. All right, so now we kind of have this like souped up version of Cayley Hamilton. All right, and I guess next time we'll do Nakayama. Are there any questions?
It's kind of a general one, isn't it? Right.
These are very general.
Oh, I mean, I have a general question.
Oh, okay.
I when I see Cayley Hamilton theorem, I think it's because my brain's already fixated on what the characteristic polynomial is. Was the characteristic polynomial came out of the theorem, or because it's
this is the characteristic polynomial right here.
That the way that you did it, right? Is that kind of how it was historic? Was he looking for a polynomial that would?
He certainly didn't do it for modules, right? So
right.
Right. So how did? Yeah, I don't know what he was. He did a ton of really crazy. So Kaylee had a bunch of really cool linear algebra stuff. I think. I don't really know. I don't know what the story behind that is.
I just always get confused because then I see, like the definite, we learn about the characteristic polynomial, and then you go, and the matrix is annihilated by it. It seems kind of like not duh, because I couldn't like prove it myself, but it just seems like it's sort of, of course it does by construction or something like that. But
I think it's I think it's a very non-obvious theory. Like it's kind of weird, right? It's like that you take this polynomial that you build from the matrix, and then it involves determinants, and then you you plug the matrix in, and then it's zero, and it is so useful, right?
So it is sort of matched in a sense, yeah. Okay.
Yeah. I think it's really neat, but yeah, I do not know what the original context was. If you guys find out, let me know. That's kind of that would be interesting. All right. Yeah. So I think we're just gonna stop the video here, and I'll stick around if you guys have any questions.
See you, Taylor. Have a good weekend.
You too.